Hi everyone, this is Dr. Ross, and I'm here to talk to you about correlation. We've been looking in this unit at relationships between two variables and a lot of their features, form, strength, direction, outliers, and we've noted that it's really important to determine a relationship's form before you think about these other things. One of the most common forms that we take a look at and that we're going to look at through the rest of this unit is linear form. When we look at a scatter plot and it suggests that we have a linear form, we can actually find a really nice numerical summary that gives us some valuable information about that relationship, about the strength and the direction of the relationship, and it's called the correlation. How do we calculate the correlation? Well, here's the formula for it. One thing to note is that we label the correlation with R. A lot of times it's called Pearson's R, and we can see that the formula is kind of a big nasty looking thing, and so it's actually a lot of work to calculate by hand. I'm not here to walk us through that, and I don't expect you to have this formula memorized, but I do want to point something out about this formula, and that's kind of the format that it has. It's adding up a bunch of stuff on the top and then dividing by the number of things that we added up. So you add up n things and divide by n. What kind of form is that? That's actually an average. So correlation is a kind of average. What is it an average of? If we take a look on the top, we're not just adding together pieces of data, we're adding together two things that we're multiplying. What are these things? Well, this one here on the left is a z-score. We've got a piece of data minus a mean divided by a standard deviation. It's a z-score for one of the x values for one of our individuals. That z-score is telling us how far that individual's score deviates from the average x score. And the same thing on the with the y values. So we've got z-scores for both the x and the y, giving us some indications of how far those values deviate from the average, and we're multiplying those two together. So the correlation is an average of all these products of deviations from what's typical. And what that helps us understand is how far individuals tend to fall away from a linear relationship. The closer that they are to this linear relationship, the stronger this correlation is. So how do we actually go about calculating it if I'm not going to ask you to calculate it by hand? Well, there's a couple ways you should be able to calculate correlation. You should be able to calculate it with your calculator and also with SPSS. I've got a very small subset of all those ACT and GPA scores that we were looking at from a freshman class a couple years ago. Let's try and check out how we can do this with a calculator and with SPSS. I've got a TI graphing calculator here, and if you have one of these, you can follow along. If not, I highly recommend going on the Tartan and looking up your calculator and reading the directions and trying that out right now. If you have a TI graphing calculator, what you want to do is you want to press Stat, and you want to go to Edit, and you want to enter your data in L1 and L2. And so that's what I already have here. I'll give you a second to pause it and go ahead and enter those scores in there. Once your data is entered, then you want to go ahead and press Stat again and go over to the Calc menu and go down to option number 4. If you're on an 83, it might be a different number, but Lin Reg is what we want. L-I-N Reg. And so I'm going to go ahead and hit enter. Mine says tell me which lists you want, L1 and L2, and then if you want a frequency list or to store the equation. I don't want to do those things, but I want L1 and L2, and then I'm going to hit calculate. And here it is. I get this output. I get some A's and B's. We'll talk about what those are in R squared, but here's what I want. R equals 0.592. Now, take note, it's possible that if your calculator is brand new or if you've never used it to calculate a correlation before, you may only see A and B, and you may not see R squared and R. What you need to do is turn the diagnostic on. For directions on how to do that, check the Tartan, the folder with all the calculator instructions, and there's one that says TI 8384 correlation fix, and check it out there. But here's how we do it on a TI graphing calculator R is 0.592. How about with SPSS? I'm going to go ahead and pull that up, and you should too. And I'll pause to let you go ahead and enter the variables. Once you have them entered, and you can go to variable view and make sure you name them, and for sure make sure the measure is set to scale. What you'll want to do is go to Analyze, Correlate, and Bivariate is what we want. And bivariate, two variables, bivariate, and we're interested in the correlation between two variables. So Analyze, Correlate, Bivariate, and what you'll see is you'll see your variables over here on the left, and you just want to make sure you use the arrow to send them over to the right. Don't have to worry about any options. It's set for the Pearson correlation, which is just what we want, and so you can just get those guys in there and click OK. And you can see in our output it says correlations, and it actually correlates everything with everything. So ACT with ACT, GPA with GPA. We're not interested in those. We want to see how they correlate with each other. ACT with GPA, the Pearson correlation is in the top row, 0.592. There we see it again. Or you could look down here, GPA with ACT, the correlations in the top row, 0.592. It doesn't matter which one comes first, they end up with the same correlation. So that's how we can calculate it, but it's going to be important for us to understand, what is that 0.592 telling us? If we're interpreting the correlation between these two variables and it says it's 0.592, what does that mean? Correlation is a measure of how well the relationship is modeled by the linear form. And so it's a measure of how strongly linear the relationship is. If we are closer to +1 or -1, that means we have a stronger linear relationship. If our correlation is closer to 0, that means we have a weaker relationship. And we'll take a look at a little scale that can help us get a sense of that. The other thing to note is that it's also a measure of whether the direction is positive or negative. And that's pretty easy. If the correlation is a positive number, it's a positive relationship. And we can see that here, higher ACTs going with higher GPAs. Positive relationship. On the other hand, if it's a negative value, then it's a negative direction. Here's another look at the strength. We can use this little scale to help us understand what's going on. If we're in the middle here around a 0 correlation, that's suggesting that there's not a linear relationship there. As we move up into 0.25, moderately weak, halfway to 1 is a moderate relationship. Get into quite strong relationship, and all the way up at 1 is a perfectly strong linear relationship. If it's +1, that's positive. Same kind of pattern as we head down to a -1 relationship would be a perfectly negative relationship. Note that the strength is context dependent. In some scenarios, a correlation of 0.322 would look very weak, but in others it actually would look somewhat strong. So what am I talking about? For example, if you're doing a physics experiment, a 0.322 correlation might be a pretty weak showing. On the other hand, if you're doing something in the social sciences like education research, a 0.322 might actually seem like a moderately strong relationship and something to take note of, just because so many other things have a lot lower correlations. In the end, for this class, you can use this scale consistently to help you make those judgment calls, and as you work into your specific field, you'll get a better sense of any kind of relative judgments that you need to make. Right now I want to show you some scatter plots and what the corresponding correlations look like, so you can get a little bit of a sense of how these fit together. Here are some scatter plots we've actually looked at before. The Maryville College freshmen from a few years back, their ACT coming in, and their GPA after their first year. And we can see a clear upward trend, and we see the correlation suggests a moderate to moderately strong correlation and positive. So 0.95, it's above halfway. It's not a weak correlation. It's at least moderate to moderately strong. Very, very similar number for another one we've looked at. In lab number 1, we looked at carbon emissions in the parts per million and how that relates to the annual temperature at the South Pole. And even though we see scatter there, this comes out to be a moderate relationship here. And so it's not a weak relationship. It's above halfway, so it's moderate, and once again, it's positive. We're going uphill. Here's one that's a very, very clear, strong relationship. You look at this graph, and it looks like a line to us. This is city miles per gallon cars got and highway miles per gallon. Very clear linear relationship here, and the correlation turns out to be very, very close to 1, which is a perfect line. So we've got just a little bit of scatter, and we see a 0.99 correlation. Once again, positive. Here's a negative one, definitely going downhill, and we see our correlation turns out negative. This also suggests that it's quite strong, right? 0.8 is close to negative 0.1, negative 0.8 close to negative 0.1. However, here's the warning. You need to look at a scatter plot first before you interpret correlation, because if we would have said this is pretty clearly a negative linear trend, and then we look at the scatter plot, we see it's not linear. It's actually a curved trend. And if we had a curved model for this, our curved model judgment would be even stronger. So the main warning there, always look at a scatter plot. Here's the other side. Here's another negative correlation and a very curved relationship, and we see this correlation turns out to suggest there's almost no relationship there. So what's the warning? If you don't look at a scatter plot, you don't know what that correlation is going to do, and so it's not informative. You need to look at a scatter plot first and decide, is this a linear relationship, and then go ahead and move on to using the correlation to help you judge the strength of it. One final point I want to make with some scatter plots, that correlation is actually very sensitive to outliers. So here's a scatter plot. I got some data from one of my early classes, the number of activities they were doing, and also the distance from their hometown when they were at Maryville College. And we can see two really clear outliers on the distance from hometown, very far away from home, and they weren't doing any activities. These other ones don't really look much like a linear relationship, hard to say, and the correlation is pretty weak. But the main point here is, take a look, this is a 0.268, so it's moderately weak. When we take away those outliers, it's gonna jump pretty far. Outliers are gone. Now this correlation jumps down to almost zero, almost no relationship at all. And if I look at this data, it certainly looks like there's almost no relationship. Just 2 points of data change that correlation almost a quarter of the way that it could even be changed. So it has jumped from negative 0.26 to negative 0.04 just from 2 outliers. The main point is correlation not resistant to outliers at all. Why does that make sense? Well, what's correlation based on? If we think about that formula, it's based on z-scores. Z-scores are calculated by using means and standard deviations. And means and standard deviations are sensitive to outliers. So if we make a compounding of all kinds of calculations based on means and standard deviations, the result, the correlation, is definitely going to be sensitive to outliers as well. So another reason why to look at a scatter plot. You got to see if there's any outliers there that are causing changes in your correlation. So summing up, correlation is an average of the products of the z-scores, how far things are from average. The correlation near 1 indicates the data falls near a line, a strong linear relationship, whereas near 0, not a strong linear relationship. Positive correlation indicates positive relationship, and negative, a negative relationship. And also take note, correlations are highly influenced by outliers. A couple other things to take note. Correlation doesn't distinguish between explanatory and response variables. We saw on SPSS output, it didn't matter which variable came first, they both gave out the same correlation. However, it only works with quantitative data. So we had to set those measures to scale. Correlation only works with numbers, it doesn't work with categorical data. Statisticians have developed other techniques to work with other kinds of data, but correlation doesn't. Linear transformations don't affect correlation, so if we standardize a set of data, it's not going to change the correlation. Correlation is never greater than 1, it's never less than negative 1. So if you are calculating your correlation for a quiz or a test and you get something that's bigger than 1, that should be a red flag, and you should know, hey, something went wrong, I need to go double check. Correlation doesn't describe forms other than linear. We saw that. If it's a curved relationship, correlation is not a good measure to use. And it never completely describes a relationship. You never just want